So now that we talked about the chemical equations and all the elements of the chemical equation as far as reactants, products, and special conditions, let's now try to put that in practice and work on balancing chemical equations. Now, the reason why we balance the chemical equation because we need to make sure the number of atoms on both sides of the equation are equal. So if you start with an X number of a specific element in your reactant side, you must have the same number of atoms on your product side. Okay. Now the reason for that is because we need to always consider um, these two factors. First, atoms are neither created nor destroyed, but they simply change partners. So bonds are broken and new bonds are formed. The count of atoms on both sides of the equation, in the input or the reactants and the products has to be equal. If it's not equal, then at that point we'll start using the coefficients by adding coefficients on both sides, either the products or the reactants, to make sure the number of atoms is equal. So the coefficients we place in front of one or more formula in a chemical equation balance the number of atoms. So we're balancing the number of atoms every time we multiply by a coefficient in the products or in the reactant side. So that one equals the number of atoms of a particular element. So they are equal on both sides of the arrow. All right, let's take an example. So, for instance, this is the common equation of water formation that we talked about earlier, where you have hydrogen and oxygen reacting together to form a water molecule. Now, if we break this down and we try to count the number of atoms on the reactant side, we notice that the hydrogen um, counts as two atoms, and the oxygen also counts as two atoms. Now, the reason for that is because we are looking at the subscript down here. And if you remember this, that the subscript represents the specific number of atoms within that molecule. Okay? On the other side, however, if you look at the water molecule, we see that the hydrogen, for example, is two. There are two atoms of hydrogen based on the subscript that is adjacent to the hydrogen symbol. On the other hand, the oxygen, because there is no subscript next to the oxygen, so there's one count of oxygen atoms. So by looking at this equation, we can determine that this equation is in fact imbalanced because the count of atoms for the oxygen in the reactant side, as you see here, counts for two atoms. And on the product side, there is only one atom for oxygen. So there's a deficit basically of one atom of oxygen on the product side. And that makes no sense because, as we said earlier, atoms in any chemical equation or in any chemical reaction in general are neither destroyed nor created. So if I started with two oxygen, I'll have to finish with two oxygen. So let's try to figure that out and see how we can make sure the count of oxygen atoms on both sides is equal. So what we do in this case, we add a coefficient to show that there are two oxygen atoms in the product side. So if you're looking at the water molecule right here, the only way to make the oxygen molecules count as two is by adding a coefficient um, next to the water molecule molecular formula. Okay? So by adding a 2 right here, this makes the oxygen in the water molecule counts at 2. Um, the moment that you add a coefficient on either the product side or the reactant side, you will have to start counting your atoms one more time because what happens, this 2 here doesn't only apply for the oxygen, it also applies for the hydrogen. So this will impact the total count of atoms for hydrogen on the product side. So to be on the safe side, what we need to do, once you add a coefficient on either side, you need to start counting your atoms for all elements in the chemical equation one more time to make sure that you are not you're not imbalancing one of the elements in the chemical equation. Okay, so if we do this one here, let's count our atoms one more time. For the hydrogen, there is two. For the oxygen, there's two. This never changed because we didn't add any numbers on this side, on the reactant side. On the product side, however, things are different. Because for the hydrogen, it's no longer a 2. In fact, it is now a 4 because this 2 here is multiplied by the subscript of the hydrogen atom. So that makes it a 4. Oxygen is now in fact a 2 because the coefficient that we added um, multiplies to the count of atoms for the oxygen in the water molecule, and that makes it a 2. So um, what we did basically, we took care of balancing the oxygen molecules, but at the same time, we have now hydrogen that is not balanced. So now we have to start again and try to balance the hydrogen molecule, or the hydrogen atom, I should say. I'm sorry. Okay. So what we do essentially, we start the same process one more time. We added the two for the water molecule. What we need to do in order to balance the hydrogen atoms, we need to look at the hydrogen on the reactant side because that's the side where we have the deficit of two um, two hydrogens, right? That's what we need to do. So the coefficient now in this case will go on the hydrogen on the reactant side. Okay, so we're adding a 2 in this case. Now, if you start counting your atoms one more time, you will see that 2 times 2, that makes it a 4 hydrogen. Oxygen on the reactant side never changed, so that's a 2. If you look at the water molecule here, that's basically the same math that we just did earlier. So 4 atoms for the hydrogen and 2 atoms for the oxygen. So all in all, if we see here, now we notice that the hydrogen atoms now is a 4 on this side and it's a 4 on this side. So hydrogen is now balanced. Oxygen in the same time, there's 2 oxygen on this side and there's 2 on this side, 2 on the reactants and the product. So the oxygen is also balanced. So now we call this balanced chemical equation. Okay? All right, common mistakes, and I've seen that happening many times from different students. What they do, instead of adding a coefficient to the equation, they basically adjust the subscript on the molecule. And that what this does basically, and I know I've mentioned that before, this changes the identity of the molecule. And this is absolutely forbidden, and you can't do it in any chemical equation or even in any chemical formula in general. The subscripts, the little numbers next to the elements in any chemical formula, those are untouchable. You can't change those numbers because this will change the identity of the molecule. What we do, however, we add the numbers on both sides, which is the coefficients. So please make sure you don't do this. Because, for example, once you add the 2, in this case, once you add the 2 to the oxygen and the water molecule, so H2O2, this is no longer water. This is hydrogen peroxide. So the molecule is no longer water because we changed the molecular formula. So please do not change the subscript when you're trying to balance the equation. It might seem at first glance this is the easiest way to do, but this is absolutely the wrong way to do it. Okay? All right, let's talk it out step by steps and see how we can balance a chemical equation. So first, consider the first element listed in the first formula in the equation and balance it by replacing coefficients in the front of one or both of these formulas, just like what we did with the water molecule a second ago. If this element is mentioned, in 2 or more formulas on the same side of the arrow, skip it until after the other elements are balanced. So in this case, we will do examples, but if you have the element that is repeated multiple times on one side of the equation, I would leave that all the way to the end. Start with the elements that only been mentioned once on either side of the of the chemical equation. Those are generally the easiest to balance first. Okay. Next, what you do is moving from left to right. Repeat the process for each element by checking your inventory basically after each coefficient is added. You might need to change the number because for the element that you tried to balance previously. That is totally normal and that's totally fine. So if you add a coefficient and then you realize this number really not working out because it's throwing the number off of other elements within that formula, that's completely fine. You'll have to come up with another coefficient and I'll show you how to do it. Then start the process again. Um, then what you do is you continue the process until the number of atoms of each element has been balanced. Okay, let's now try to do our first example or our first practice to balance a chemical equation. So first, what you're looking at here, we're looking at ammonia reacting with with oxygen to form nitrogen oxide gas and also water. So first, what we need to do is we need to count our element for count the atoms of each element in this equation to find out if the number of the elements, the number of atoms, I'm sorry, on the left side equals the number of atoms on the right side. So first thing, let's do the nitrogen. So the nitrogen on the left side of the equation or on the reactant side of the equation, there is only one nitrogen. So that makes it one nitrogen. I don't have any other nitrogen in any other molecule on the reactant side, and that's something that you need to pay attention to. In other words, that if you count one nitrogen in one molecule, do not assume there is no more nitrogen in another molecule on the reactant side. So always double check if there is any other molecule that contains that specific element. Okay, let's do now the hydrogen. On the reactant side, I have 3 hydrogen right here. So that makes it 3 hydrogen. The oxygens, the number of atoms for the oxygen on the reactant side, there is 2, right? There is 2 oxygens because we have to pay attention to the subscript that we have in the molecular formula. Okay. So now let's look at the product side and let's count our atoms for the nitrogen. For the nitrogen, I have 2 nitrogens in here. Do I have any other nitrogen somewhere else? No. So that makes it 2 nitrogens. For the hydrogen, I have 2 hydrogens in here. So that makes it 2 hydrogens. For the oxygen, and that's the last thing that we have for the product side, I have 1 oxygen on this one and I have another oxygen in the water molecule. So in total, that makes it 2 atoms of oxygen on the reactants on the product side. Okay, so now what we need to do is we need to perform the stoichiometric balance to make sure the number of atoms on the product side equals the number of atoms on the reactant side. Okay, so if we started with 2 atoms of nitrogen, or if we ended up with 2 atoms of nitrogen, we must have started with 2 atoms of nitrogen. Because, as I said earlier, atoms are not created nor destroyed. We're essentially just changing partners and forming new bonds. Okay? So now let's focus on the nitrogen first, because we have it first on our list. So I have 2 on the product side, and I have 1 on the reactant side. So what I can do simply, I can just add a coefficient of 2 for the ammonium molecule, right? So at this point, this should take care of the nitrogen because the nitrogen now counts as 2. Remember, there is a subscript of 1. There is a subscript of 1 down here, okay? That's why we don't see it. So now, it's no longer a 1. It is a 2 count of nitrogens. Now, every time you add a number, what you need to do is you need to hit the reset button and start counting your atoms one more time because that 2, the coefficient of 2 that we just added here, it is going to also impact the count of atoms for the hydrogens. So hydrogen now on the reactant side, it's no longer a 3. It is now a 6. Remember, 2 times 3, that makes it a 6 atoms of hydrogen. How many hydrogen do I have on the product side? That remains as 2 because we haven't added any numbers on the product side. So the common denominator between 6 and 2, or the number that I can use to multiply the number 2 with so I can have a 6, that makes it a 3. Okay, so now 3 times 2, that's a 6. So now I have the nitrogen has been balanced. I have the hydrogen also has been balanced. Now what I need to do, I need to double check my math one more time to make sure the count of oxygen is still or has still remained the number of count of oxygen has not changed, especially after adding the three to the water molecule. So as far as the two here, this does not change. Any count of atoms for the oxygen in this case remains at two. If I look on the other side, however, it is no longer a two because I have one in here and I have a three in here. So that makes it four in total. Remember, this three here also multiplies for the subscript for the oxygen in the water molecule, and since there is only one in here, that makes it a three. 3 plus 1, that makes it 4 total. So this one here, okay, 2. This one here, it's now a 4. In order to balance the oxygen on the reactant side, what I can essentially do simply, I can just add a 2, a coefficient of 2 to multiply the oxygen molecule. So this will make the oxygen on the reactant side as 4. Okay? So now this will make, all right, let's add it up to date. So that makes it 2, 2, and there is 3 for the water. Okay? Now let's double check our math one last time to make sure that the equation is actually now, or we can describe this equation as a balanced equation. Okay? So for the nitrogen, 2 times 1, that makes it 2. Do I have any nitrogen somewhere else? No. So the total number of atoms for the nitrogen in the reactant side of the equation is a 2. On the product side, I have 2 as well. So this one is balanced. The hydrogen, I have 2 times 3, that's a 6. I have 3 times 2, that's a 6. So that makes it 6 and 6. For the oxygen, I have 2 times 2, that's a 4. And I have 1. And I have 3 times 1, that's a 3. So both makes 4. So that makes it a 4. So the nitrogen, the hydrogen, and the oxygen, they're all balanced. So this is now a balanced chemical equation. And we call this stoichiometric balance. Okay? Let's try to do a few more examples. Okay? All right, so let me just clear this one first. Okay, so what we need to do here, essentially the same strategy. We need to count the number of atoms for the reactants as well as the products. So let's start with the nitrogen. So this first step is really fundamental to make sure that you're balancing the equation correctly. If you start with the wrong count of atoms from the beginning, unfortunately, all the work that you'll be doing later it just will be worthless because you have started with a wrong count of atoms. So all your coefficients will be wrong. As a result, your balancing process will not be correct. Okay, so let's do the nitrogen. So how many nitrogens I have on the reactant side? I have 2 in here, and I have another 2 in here. So that makes it 4 count of atoms for the nitrogen. Let's do the hydrogen. How many hydrogens I have? I have 4. Oops. I have 4. And I don't see any of the hydrogen anywhere else on the reactant side. So that makes it 4. Now let's look at the oxygen. How many oxygens I have? I have 4 oxygens in here. I don't see oxygens anywhere else on the reactants in the reactants group. So that makes it 4 of the oxygen. Okay. Now let's do our count for the products. How many nitrogens I have? I have 2 only. I don't have any nitrogens anywhere else, so that makes it 2 total for the products. For the hydrogen, I have 2 hydrogens. For the oxygen, I have only one oxygen in here. So it's pretty obvious that we have deficit of count of atoms for the nitrogen, for the hydrogen, and for the oxygen. So we need to balance everything. So what I will do first, just because nitrogen does exist in two different molecular formulas on the reactant side, I'm going to leave this all the way to the end because it might be a little bit tricky to start with this one. Okay, what we do first, and that you should always follow that. You should follow that strategy. If you have an element that exists in two different formulas on either side of the product or the reactants, leave that one all the way to the end and then go back and balance that one. That way it's easier. So what I'm going to do first here, I'm going to try to balance the hydrogen. So for the hydrogen, I have 4 and I have 2. I can simply multiply the 2 by 2 and that makes it a 4. So now it is 4 count of hydrogens. Okay? Now, obviously, this does not change the count of the nitrogens because water does not have any nitrogen molecules, but will change the count of the oxygen molecules, right? So what you need to do is you need to double check your math one more time and reset your count and count the number of atoms one more time. Ideally for everything, but in this case, because we know that only the oxygen will change. But if you want to be on the cautious side, you can always just double check the count for all the elements. So that way you know for sure that you're not missing anything. So in this case, we know the count for the oxygen has changed, so it's no longer a 1. It is now a 2. Okay? So now if I come here and I try to balance the oxygen, and I have 4 on the reactant side and I have 2 on the product side, I'm still short with 2 atoms of oxygen on the product side. So what I need to do, unfortunately, I'm going to have to update this 2 that I just added, the coefficient of 2 that I just added in here, and this must be a 4 in order for the oxygen to balance the count of oxygen on the reactant side. Okay? Now, what this will mean, this is going to change the count of atoms for the hydrogen. Because hydrogen now is no longer a 4 as we did initially when we multiplied with a coefficient of 2. It is now, however, 8. So that makes it 8 hydrogen. But you get the idea. You add that coefficient, you double check the math. If it doesn't really add up, you have to restart again and add the new coefficient and make sure that numbers matches up. Now, I can tell you for sure, I'm not going to give you something that it's 5 layers of complicated process or, very complicated chemical, like a stoichiometric balance. I'm going to try to keep it as simple as possible. So you guys don't have to go stir crazy trying to figure out what is the number. But in general, I would like you to get used to this idea of trying to add a coefficient for the first time and then multiply your numbers. And if it doesn't really add up, that's okay. Start again until eventually you're going to make sure all the count of atoms is balanced on both the reactants and the product side. So in this case, let's go back to this one. So the oxygen now is balanced. And the count of hydrogen now is 8. So what we need to do now, we need to balance the hydrogen on the reactant side because that's what we are short as far as count of hydrogens. So what we can do, since I have a 4 in here, I can multiply that by 2, and that should make it 8. So now oxygen is balanced, excuse me, and hydrogen now has been balanced, okay? So what we need to do now here at last, we just need to check the count of atoms for the nitrogen. So for the nitrogen now, I have 2 times 2, that's a 4, and I have another 2 in here. So now we need to update this and makes it a 6. So my total count of atoms for the nitrogen on the reactant side is a 6. Now I have only 2 in here, so that should be an easy peasy because I can just multiply that 2 by 3 and that will make it a 6. So now all the elements in this equation has been stoichiometrically balanced. In other words, that if you multiply the coefficients by every subscript for these elements, you will end up with the same number of atoms on the reactant side as well as the product side. Let's double check this one. 6, 6. There is 8, 8. There's 4. There's 4. There's 3. There's 4. And there's 2 on this one. Okay? So let's do the math one more time, and you should do this also in the exam as well as the practice problems. Always double check your numbers at the end. Starting with the nitrogen here. So 2 times 2, that's a 4. Plus 2, that's a 6. So that makes it a 6. 3 times 2 is a 6. So nitrogen is balanced. Let's look at the hydrogen. 2 times 4, that's 8. 4 times 2, that's 8. Hydrogen is balanced. For the oxygen, I have 4 in here, and I have 4 times 1, that makes it a 4. So the oxygen is balanced as well. So this equation now is stoichiometrically balanced. Now let's try different strategies when it comes to balancing equation, because sometimes might get a little bit more complicated. And if you get used to these strategies and try to apply them with examples, homeworks, I think you should be able to balance any type of chemical equations, regardless of how complicated it is. Okay. So first, what you can do is we can use what we call it the swapping strategy. So sometimes it is very hard to find a common denominator. I mean, earlier in the first couple examples, it was so easy to find a common denominator. For example, between the 4 times 2, which is 8, and you have 4 hydrogens on this side, so you can just multiply that by 2 and it'll give you 8. So finding a common denominator in this case, can be really easy. In some cases, like the one that you're looking at right now, when you have 4 phosphorus, 8 sulfurs, to form phosphorus sulfide, I think it's going to take us a really long time to try to figure out what is the common denominator between 3 and 8. That really can take us forever to figure that out. But what we can do is we can use the subscript on the product, on the reactant side, and consider that as the coefficient, and use it to multiply on the product side and use that as our coefficient. So in this case, in this specific example, you can use the 8 for the sulfur and consider that the coefficient for the products and multiply that by the subscript here for the sulfur. So the 8 times 3, that's 24. And you can do the other way alternatively. So multiply the 3 times 8, that makes it 24. Now, as far as sulfur, 8 times 4, you can just multiply that 8 times 4. Okay, so 8 times 4, that's 32. 8 times 4, that is 32 of the sulfur. For the phosphorus, I'm sorry. 3 times 8, that's 24. And then 8 times 3, that's 24 for the sulfur on the product side. So the first tip here, that if you can't find a common denominator, like the 2 and the 4 and 2s, between the 8 and 2 there's 4, between the 6 and 3 there's 2, so on and so forth. If it is two numbers that are really unrelated to each other, what you can do is you can use the subscript and consider that as a coefficient on the product side, and you can do the same thing on the reactant side. Okay? And that's what we did here with this example. So you can do 8, you can do 3, and you can do 8 in here. The number of atoms here will be, here will be 4. Well, later on will be 32. I'm sorry. This will be 32. 32. This will be 24. This will be 24. And the equation now has been stoichiometrically balanced. Okay? That's tip number 1. Tip number 2, what we can do is we can use the fractions. And there are conditions where you can use the fractions. Okay? First, it has to be a pure non-metallic compound. And if you remember our non-metal buddies from the periodic table, which is the nitrogen, the hydrogen, the oxygen, the carbon, so on and so forth. But in this case, we're talking about the diatomic non-metals, which is the hydrogen, the nitrogen, and the oxygen. You can use the fractions because what fractions help us with, it helps us to introduce single atoms when we're trying to do stoichiometric balance. So previously in all the balancing that we've been doing, every time when we add a coefficient, we either multiplying by a factor of 2 or multiplying by a factor of 4, so on and so forth. When you use a fraction with diatomic non-metallic molecules, what you can do is you can actually introduce a single atom into your into your equation. So this can be a really helpful tool. Now later on, you can get rid of the fraction. You can by just multiplying by the denominator of that fraction. Let's do an example so it can clarify things. Okay. Um, so let's do our count of atoms for the aluminum. For the aluminum, I have 1 on the reactant side and I have 2 on the product side. For the oxygens, I have 2 and I have 3. First, what I will do is I'm going to try to balance my aluminum. I have 1 on the reactant and I have 2 on the product. What I can do is I can just multiply the aluminum in here by a factor of 2. So that makes the count for the aluminum 2. Now the aluminum, I'm sorry, it's been balanced. Okay. Now if I look at the oxygen now, and I'm trying to balance the 2 of the oxygens and the 3 of oxygens on the product side, I can't really find any common denominator in this case between 2 and 3. Okay, so it's a deadlock at this point. However, we can use a fractions. Fractions can help us convert the diatomic molecule for the hydrogen um, into either an odd or an odd number most of the times. Okay, so what I can do is I can multiply this by 3 halves. Okay, what happens, and this is a pure math. We're not doing any chemistry at this point, to be totally honest. The 2 is going to cancel out with a 2, and now I'll have 3 oxygens equals 3 oxygens on this side. Okay, so first question, how would I know that it's time for me to use a fractions? Okay, do I need to use a fraction or do I not need to use a fraction? Your first signal or your first indication to use a fraction, if you have something like hydrogen, oxygen, nitrogen, if you have those three molecules, there's probably a good chance that you will need a fraction to do the balance. Not always, but you should consider that in. Okay. Now, if you put your initial count of atoms for the products and reactant, and you notice there is a shortage of 1 atom on either side, the products or reactants, and that's your chance to use the fraction. Because every time you use a coefficient that is not a fraction, you will be either multiplying or tripling that amount or quadrupling that amount. But with a fraction, you can add single atoms. Okay. So if you look at this oxygen here, this basically meets all the conditions that I just mentioned earlier. There is an oxygen. There is a deficit of 1 atom on the reactant side. So it screams at me right there that I need to use a fraction. Okay. So I multiply that 3 halves. Like I said earlier, the 2 cancel out with a 2. Then I will be left out with the 3 oxygens. So now there's 3 oxygens. Now, if I want to, all right, let me clear this off. So there is 2 aluminums and there's 3, 2. Now, in a stoichiometric balance, we can't have fractions. So what we need to do is we need to get rid of this fraction. The way to do this, you'll have to multiply both sides of the equation with the denominator of that fraction. So that's a 2, then I'll have to multiply by 2. Okay? So the final equation would look like this. 2 after multiplying by 2, this will look like 4, 3, 2. Now, if you double check your count of atoms on both sides, aluminum, I have 4, and I have 4. That's 4. For the oxygen, I have 3 times 2, that's a 6. And I have 2 times 3, that's a 6. So both are equal. then this equation is considered stoichiometrically balanced. Okay? So tip number one, you can use the swapping if you can find a common denominator. Tip number two, you can use a fraction if it is an oxygen, hydrogen, or nitrogen. And this is basically more of the rules about the fractions, and it tells you exactly when and how to use the fraction, and it's just uh, it explains exactly what we just did in this example. Now as far as a fraction, now mathematically speaking, again, this has nothing to do with chemistry because obviously when we do the fractions, we are not chemically splitting the molecule. What we are doing is we're just using the math technique to help us out have the same count of atoms on both sides. So what you are doing, and the reason why we can only use it for hydrogen, nitrogen, and oxygen, and we can't use it for something like carbon dioxide. Okay, so what we are doing essentially, and again, mathematically speaking, when you multiply that by half, you're basically splitting this just like this. So you will end up with just one molecule of oxygen, or I'm sorry, one atom of oxygen, right? If you have three molecules, if you have three molecules of oxygen and you multiply and you do three halves, what you are doing is you're basically splitting up, and again, mathematically speaking, all these molecules of oxygen, and you are forming only three oxygens instead of having six oxygens. Okay? The reason why we can't do it for something like carbon dioxide, but there's no way you can split that from the center. You have the carbon right in the center. Okay? So that's when it comes to using the fractions. So now let's try to balance a chemical equation with polyatomic ions. So the term polyatomic ions, you guys should be familiar with this at this point, okay? Because we did talk about polyatomic ions when we discussed the periodic table, when we talked about bonding, chemical bonding, covalent bonding, so on and so forth. And here's the list of our polyatomic ions. And at this point, I expect everybody to know the name as well as the structure for these polyatomic ions, because in the next exam, I'm not going to be providing this list to you. You should know the names and the molecular structure. So when it comes to balancing a chemical equation with polyatomic ions, there are two different ways. There is the hard, long way, and there is the easy, short way. I think it makes more sense to do the easy way, right? And that's what I will do in the next attempt. But first, what I will do, I'll show you the long way that I think that you guys should try not to do, because it's trap for making mistakes. There's so many counts, and you can easily forget one of those elements. Okay, so let's do it the first. Let's do it the first time with a long way, and I know you guys are probably gonna stick with the easy way. Okay, so when we are trying to balance this, we are going to go just like how we have been doing with the previous examples, which is counting your atoms. So first I'm going to try with the zinc. I have one zinc on this side, and I have three on the product side. Okay. For the nitrogen, I have two, right? Because the two is outside the parentheses applies for the nitrogen inside the parentheses. So that's two nitrogen. Do I have any nitrogen anywhere else in my reactants? The answer is no. So my total count of nitrogens in the reactant side, it's only two. Let's look at the product side. I have only one nitrogen, which is right here. Okay. Let's count our oxygens. Oxygen is 2 times 3. So that makes it a 6 of oxygens within the zinc nitrate. But if you look at the sodium phosphate, there's another 4 of oxygens in here. So 2 times 3, that's a 6 plus 4, that makes it 10 of oxygens on the reactant side. On the product side, I have 2 times 4, that's 8 plus 3, that's 11. Okay? So I have 10 oxygens on the reactants, and I have 11 on the products. Let's count our sodiums. On the reactants, I have 3 sodiums. That's right here. Do I have any sodiums anywhere else? The answer is no. Let's look at the product side. I have only 1 sodium right here. So that makes it 1 sodium. Okay? All right, lastly, the phosphorus. How many phosphorus I have on the product with the reactants? I have only 1 phosphorus right here. So that makes 1 phosphorus. On the product side, I have 2 phosphorus. So that makes it 2 phosphorus. Okay. Okay, let's follow the same strategy that we have been doing. We're going to start with the zinc and make sure that the number of zinc on the reactants equal the number of zinc on the products. Okay, so I have 1 and I have 3. So easy solution for this, what I can do, I can just throw a 3 as a coefficient for the zinc nitrate. So that makes it 3 for the zinc. Now it is a 3. So the zinc now is balanced at least up to this point. But this 3 here, as you well know at this point, it's going also to apply for the nitrogen. It's also going to affect the oxygen count. Okay, so we need to update those numbers. So for the nitrogen, we have 2 nitrogen times 3, that makes it 6 now. Okay, for the oxygen, I have 2 times 3, that's a 6, times 3, that's 18, plus 4, that makes it 22 count for oxygens. Okay? Now, does any other number changes in here? Does my products count change? Not at all, because we didn't really add any numbers. We didn't really factor any coefficients at this point for the product. So you don't have to worry about counting your products, and I think this makes sense to you at this point. Okay? The sodium also doesn't change because this number does not really affect the sodium. The 3, right? We're talking about the 3. And the phosphorus does not change as well. Okay? So now what we can say that zinc has been balanced, and now let's try to do the nitrogen. So just pay attention to this, please. When you add a coefficient, you'll have to count your atoms one more time to make sure that you're updating your inventory of atoms count. Okay, this is really important. I don't want you to get caught up with just adding coefficient without double checking your numbers. Let's do the nitrogen. So for the nitrogen, I have 6 on the reactant side, and I have 1 on the product side, right here. So what I can do is I can just multiply the sodium nitrate with a 6. So this takes care of the nitrogen now, and the nitrogen now is 6. So the nitrogen is balanced. So I have the zinc up to this point is balanced, the nitrogen is balanced. But as you guessed it, the 6 here also changes the count for the oxygen, changes the count for the sodium. So now I have to really pay attention to this. So first, I'm going to update the count for the oxygen on the product side. So 6 times 3, that's 18. 2 times 4, that's 8. So that makes it 26. So we have shortage of oxygens now on the reactant side. So what we can do is we can multiply the sodium phosphate with a coefficient of 2, and that should bring up my count of oxygen now to 26. Let's double check that. So 2 times 3 is a 6, times 3, that's 18, right? 2 times 4, that's 8. 8 plus 18, so now it is 26. Okay? So now my oxygen is also balanced. So I have 26, 26. And this one is 6. This one is 3. Okay. Now let's count our sodium. Make sure that the sodium is balanced. So sodium on the reactant side, 2 times 3, it's a 6. So it is now a 6. On the product side, 6 times 1, so that's a 6. So the sodium now, coincidentally, it's balanced as well. Let's look at the phosphorus. So for the phosphorus, I have 2. All right, let's clear this one up a little bit. Okay, so there is a 2 in here. So for the phosphorus, I no longer have a 1. It is now 2. Okay, so it's 6, and this one is 2. For the phosphorus in here, it's already a 2, so it's already balanced now. Okay, so Let's make it look nice and neat. Okay, this is 2, and this is 3. Okay. Let's clear this one, and that's a 2. So now if you double check our math, 3 for the zinc, 3 for the zinc. For the nitrogen, I have 6 for the nitrogen. 2 plus 3, 2 times 3, that's a 6. So it's 6 in here. For the nitrogen, I have 6, so it's balanced. For the oxygen, I have 2 times 3, that's a 6 times 3, that's 18, right? 2 times 3 times 3, that's 18. We have another oxygen in here, so 2 times 4, that's 8. 8 plus 18, that's 26. And the same deal on this side, so the oxygen is balanced too. For the sodium, I have 2 times 3, that's a 6. And I have 6 in here, so the sodium is balanced too. And the phosphorus at the end, it's 2, right? Because the coefficient of 2 here applies for the phosphorus. So 2 on this side and 2 on the product side. So now this equation is balanced. So this is the long way of doing it. The easy way of doing it, what you can do, instead of splitting up your polyatomic ions, you can basically keep them intact, okay? But before we do that, let's do a quick refresher, because I know we did a practice on this a couple lectures ago, that we can basically try counting our atoms by multiplying with a coefficient to make sure that our count of atoms is correct. Okay, so in this case, the calcium carbonate, the 2 here, and this is what we have been doing for the past few examples and even before lectures ago. So 2, the coefficient of 2 applies for the calcium and applies also for the carbon and for the oxygen. Okay, but because the carbonate is a polyatomic ion, you can essentially consider that as one entity, and you can treat it as one unit instead of splitting into carbon and oxygen. Okay, so what I can say calcium. I can say calcium now counts as 2 because this multiplies by 2. And instead of saying carbon is now 2, oxygen is now 6, what I can say, I can keep the carbonate together and call that carbonate ion and just multiply that by 2. Okay? Same thing with a calcium nitrate. And instead of splitting the nitrogen, and instead of splitting the oxygen, what you can do is you can leave the nitrate ion as one unit and multiply that by 2. Okay? So instead of saying 4 and 6, 4 for the nitrogen, 6 for the oxygen, you can just multiply the coefficient of 2 by the 2 on the parentheses and call it 4 polyatomic ions of the nitrate. And I think that's a lot easier. I think that this will cut your time by almost half when balancing an equation with polyatomic ions. Okay? Let's practice. So instead of, like I said, instead of splitting all these polyatomic ions, I'm keeping them as one unit. So the nitrate and the phosphate, I'm keeping them, as one piece. So let's do our count. For the zinc, I have 1 of the zinc on the reactants. All right, let's make this on the side so we can make some room. There's 1, and that is 3 on this side. For the nitrate, again, I'm taking everything inside the parentheses. So that makes it 2 of the nitrate, and that makes it 1 of the nitrate. For the phosphate, I have 1 of the phosphate, and I have 2 of the phosphate. For the sodium, I have, my parentheses here, I have 3, and I have 1. Okay, let's try to balance it just like how we did the other one. So for the zinc, I have 1 and I have 3. What I can do is I can multiply this by 3, so that makes it 3. For the nitrate now, so the number is no longer a 2 because it's 3 times 2, so that's a 6 now. Okay? I have 1 of the nitrate in here, so I can just multiply that by 6. So it is now a 6. For the phosphate, and again, you'll have to double check your math, but I'm not doing it here because at this point I think it's you guys get the idea. But during the exam, please, you have to double check your count of atoms every time you add a number. Okay, for the phosphate, I have one of the phosphate, and on this side I have two of the phosphate. So what I can do is I can simply add a 2 on this side. So it is now a 2 of the phosphate. So the phosphate now is balanced. Okay? For the sodium, I have 2 times 3, that's a 6, and I have 6 in here. So there is 6 and there is 6. Okay? And now this equation has been balanced, and it's the same conclusion as the first one. It's just much less time because instead of counting for the oxygen, and instead of counting for the oxygen, for the nitrogen, for the phosphorus, for the oxygen one more time, and if and you have seen how complicated it can be when you have 2 times 3, 3 times 2, and you have to multiply all these numbers together, chances of making a mistake is really high. So I highly recommend being familiar with the polyatomic ions and try to keep the polyatomic ions as one piece when trying to do stoichiometric balance. I think it's a lot easier. I think it makes more sense. And it does prevent you from making mistakes. Okay? And here's the list of common polyatomic ions. So at this point, this should take care of the stoichiometric balance. Now we are going into precipitation now reactions. That we learned how to balance chemical equation, and we learned about the stoichiometric balance, let's try to incorporate that concept into the next topic, which is the precipitation reactions. Now, generally in chemistry, the reactions are described based either on the products or based on the reactants that are involved in their reaction. So, for example, later on we will look into neutralization reactions, which where you have acid and base reacting together to form salts. Now, what we will be looking at, we'll be looking at precipitation reactions, which means these are kind of reaction that, when it takes a place, a sol- excuse me, a solid precipitate will be forming in the reaction medium. Okay, so before we do any examples, let's first get introduced into some definitions. First, a precipitant, it's to cause a solid substance to be separated from solution. So we will see that I think in couple labs, in couple labs to come, that when you react two salts together, all of a sudden, white solid material start forming in the solution, and later on, this material starts settling at the bottom of your solution. So we call that a precipitant. So to cause a solid substance to be separated from solution, which means you'll have two phases. You'll have a liquid phase and you have a solid phase at the bottom of the solution. A solution is a homogeneous mixture of two or more substances. So for example, if you drink coffee and you add a creamer, that is a solution. So the coffee and the creamer is considered a homogeneous solution because at some point, I mean, at first, maybe once you add the creamer, you'll see some kind of phase separation. But once you start shaking the solution, it gets homogeneous, and the creamer is no longer separated from the main ingredient, which is the coffee. Okay, so that's in terms of solution. Solute is a substance that is dissolved in another substance, or another way, we can consider this the minor substance in your solution. Okay, so the minor substance that is considered the solute. The solvent, it is the major substance. So going back to the example of coffee and a creamer, the coffee will be basically the solvent, and the creamer will be the solute. Okay, so the solvent is a substance in which another substance is dissolved. Aqueous solution is a solution in which the solvent is water. So in any reaction where the medium is water, we consider that one as an aqueous solution. Okay, so you have the material, the solute is completely dissolved, in most cases as a solid, and then when it dissolves, it forms cations and anions, and we call that as an aqueous solution. Okay, so these are some of the terms that we will be going over during precipitation reactions. Okay, I would like you to be familiar with all these because I may well ask you during the exam about some of those as definitions. Okay, so a solute is dissolved in water. So the solute is said to be this. It is soluble in water. Okay, so once dissolved, that's the difference between a precipitation reaction or a precipitant and a dissolved matter. So a precipitant is a material that it's not soluble in the solvent. A dissolved material or a dissolved matter in water, that means it is considered a soluble material in water. Ionic compounds, as I said earlier, are often formed cations and anions, or in other words, it is considered a soluble material in water. Okay, and generally, when you have these materials, when you have these ionic compounds dissolved in water or soluble in water, these particles are so evenly distributed that the relative concentration of these compounds throughout the solution or throughout the solvent water is essentially the same. Okay. Big example. So if you have a cup of water and you add a few grains of salt, or maybe like a spoon or two of salts, and you start stirring to make sure everything has dissolved, at some point, it doesn't matter from which spot of your solution you're trying or you're getting your sample, that container or that solution will all taste salty at some point, and the concentration is evenly distributed. So let's look again and see what a homogeneous solution actually means, or how the homogeneous solution would look like. So if we look at a solution of water and salt, and that salt can be something like an ACl, and we know an ACl dissolves in water. Once the solute is completely dissolved in the solvent, which is the water, all the cations and the anions, like the chlorine anions and the sodium cations, travels all across the solvent in a way that makes the concentration of the salt equally the same from either side or from any spot that you would like to take a sample from. So sorry about that. So let's assume that you're trying to get a sample from here. This corner right here will basically taste as salty just like as the sample from up on the surface. That's because all the cations and anions are evenly distributed throughout the sample, and that's what happens um, in ionic compounds that dissolves in water. Okay, and we call that homogeneous solution. Now, the opposite of a homogeneous solution is a heterogeneous solution. And in that case, we're talking about precipitant. Okay, but homogeneous solution, that's basically the idea, and that's what I would like you to know about homogeneous solutions. Okay, when it comes to solubility in water, I think water is a pretty incredible molecule. The way that it behaves, and that the way that it basically dissolves the ionic compounds in general, and that's because of its unique polar molecule covalent bond. Now, if you remember back when we talked about covalent bond, there is the polar and there is the nonpolar. And when we talked about the polar, and I want to focus on this one because water is a polar molecule. In a polar covalent bond, you have one side of the bond where you have relatively more density of negative charge, aka electron, and you have on the other side relatively less density of electrons, or less density of negative charge, which makes one side partially positive, and makes one side partially negative. This is basically the secret for water being so powerful to dissolve ionic compounds, because the partially positive charge grabs the negatively charged particles, or the anions of the ionic compounds. The partially negative charge side of the polar bond will grab on the positive particles of the ionic bond, or also the cations. Okay, and that what makes the water such unique in dissolving ionic compounds, because of the partial negative charge and the partial positive charge, and that's due to the nature of its covalent bond. Now, in the meantime, water molecules connect to each other. I don't want to call it bonding because really it's not a bonding. It's basically just a connection to form the water structure The partial positive charge on the hydrogen would form some kind of connection with a partial negative charge that rests on the oxygen in this case, and so on and so forth. So you will have another dotted connection between another hydrogen and another water molecule. Let's now take a little bit of a deeper dive into the solubility of water and salt, something like NaCl, which is going to be our case study for a while. So this is NaCl. And to try to see how the mechanism of the solubility actually take place between water and ACl. Now, if you remember from the previous slide, we have the water molecule, the polar covalent bond of the water molecule would look like something like this, with the hydrogens on both sides, the two non-bonding pair of electrons, and you have a partial negative charge on the side due to the electron density that we have here. And we have a partial positive charge on the hydrogen atoms due to the deficit or the shortage of the electron density. Okay, so most of the electrons, if you remember, most of the electrons is being withdrawn toward the oxygen right here, and that explains the partial negative charge on the oxygen. That's due to the high electronegativity of the oxygen compared to the hydrogen. Okay, so that's just a side note. So if we go back to the NaCl, our buddy, we know that NaCl is ionic compound, which means when we say ionic compound, that means we must have cations and we must have anions, right? Actually, let's do it the other side. So we have cations, which is the Na, and we have Cl, which is the anions. What happens with water and its partial negative charge and partial positive charge, it starts grabbing on these cations and anions and start basically snitching these cations and anions from the NaCl molecule. And that's what we see here in the early stages, okay? So it happens first with a single sodium and a single chloride, and then it propagates into the next sodium and the next chloride, the next sodium and next chloride, so on and so forth, until eventually the whole mass of the NaCl disappears and it turns into an aqueous solution of Na positive, of Na cations, and chlorine anions distributed throughout the solution of water. Okay, so this is how the solubility of NaCl in water basically take place. So in a later stage, what we notice that chlorine, which is the green big atoms here with the electron, with a high electron density, right? This is the anion. And if you also pay a close attention, you notice that the small little hydrogen, the black globes that you see here, those are the ones that are basically trying to bond or trying to connect to the chlorine anion, because this is the partial positive charge, okay? So that is the positively charged hydrogen, the partial positively charged hydrogen. On the other hand, if you look at the sodium, which is right here, the cations, you can see the larger red globe, which is basically the partial negatively charged oxygen, and that's what's trying to basically connect to. Okay, now all the cations and all the anions as well, they are evenly distributed throughout the solution, which means we have a homogeneous solution in this case. Okay, so this is how the solubility process take place. Now let's look into precipitation reactions, and that should basically, all these concepts that we covered should help us understand a precipitation reaction and why a precipitate forms in some cases and why in some cases it is considered an aqueous solution. It's all and it has reached a complete solubility. Okay, so precipitation reaction is also known as double displacement reaction. Now, why do we call it a double displacement reaction? That's because you have two events of displacement of two cations and anions switching partners. Okay, so in this case, if you're looking at A and B, a salt that has A and B partner and C and D partners, what happened, A and D forms the bond and B and C forms the bond. Okay, so you can write it this way, which is also can be an easy way: A, B, C, and D. So you have A and C, oh, I'm sorry, A and D will bond together, and B and C will bond together. So you form, what are you essentially doing? We're forming two different salts from a new bond formation between the two anion between the anions and the cations. Okay. Now the reason why we call it precipitation reaction, because there are times when the salts that are formed in here can be insoluble in water. When we say insoluble, that they will carry on the symbol of S. Now, I don't want you to misconcept the S with soluble. S means solid. Okay, so every time you see a salt, in a salt or any other type of molecule in a chemical equation that has S between parentheses, that means it's a solid. And we talked about this when we talked about S means solid. We talked L about, we said L is liquid. G means it's a gas. AQ means it's aqueous. Okay, so S means it's solid, means it's not soluble, means it's a precipitate. Okay, so let's talk about precipitation reactions. Okay, so sometimes a double displacement reaction has one product that it's insoluble in water. This type of reaction is also known as precipitation reaction. So when a reaction forms a material that is not soluble in water, and that would be clearly seen with a solid material settling at the bottom of the solution, we describe that as precipitation reaction. As that product forms and it merges or it precipitates, it forms from the solution as a solid. So as I said earlier, it will form as a solid material on the bottom of the solution. The solid product, it's also known as a precipitate. Okay, so when you look at this equation right here, this is AQ, means it's aqueous, means it's soluble in water. Same here with the sodium carbonate. When you look at the calcium carbonate, however, you can see S letter, which means it's solid, which means it's not soluble in water. So my precipitate in this reaction, this is my precipitate in this reaction, which means the material that is not soluble. So now let's try to understand precipitation reactions so that way we can describe reactions, describe also the final mixture, the final product, and also try to predict solubility when two compounds are reacting together. Um, let's look at an aqueous solution of calcium nitrate. This is very similar to the NaCl that we looked at earlier, where you have the cations, which is the calcium 2 plus, and you have the nitrate, which is the polyatomic NO3 negative. Okay, what basically is happening? You have the cations forming a very weak bond with a partial negatively charged oxygen. Okay, remember this, negatively charged, and this one is positively charged. So the calcium is going to form a weak bond with the oxygen, excuse me, and the nitrate here is going to form another weak bond with the hydrogen. And that's how the aqueous solution is going to basically to happen. It is a homogeneous solution where you have all the cations and the anions evenly distributed throughout the solution. Okay? Very similar to NaCl. Now the case is different once you introduce another salt into this mixture. And in this case, what we're adding sodium carbonate or Na2CO3. Now, sodium carbonate, it is also an ionic compound, correct? Because sodium is from the first group in the periodic table, and those guys always form ionic compound. Well, what does it mean when we say ionic compounds? That means we have sodium cations and we have carbonate polyatomic anions. Okay? Now remember, when we're talking about the water molecule, it's partially partial positive charge on the oxygen, partial negative charge on the oxygen, and partial positive charge on the hydrogen. Okay? So what happens once you start introducing a new positively charged particles and negatively charged particle, you will have a fierce competition between the negative charge in here and the positive charge in here, and the positive charge on the cations and the negative charge on the anions to compete to grab the positive charge and the negative charge on the calcium cations and the carbonate cations. Or the nitrate cations, I'm sorry. The nitrate, I'm sorry. The nitrate cations. So the sodium is going to compete with the hydrogen to form another bond with the nitrate, and the carbonate it's going to compete with the oxygen here, the partially charged oxygen, to grab on the calcium. But because of the overwhelming size of the positive charge and the negative charge on the cations and the anions of the carbonate and on the sodium, it will outcompete and it will break the bond between the oxygen and the calcium and the hydrogen and the nitrate, and it forms, which would result in forming Na and new compounds, NaNO3, and calcium calcium carbonate. So remember, let's take a look at this one more time. We have O, we have H, we have the negative charge, we have the positive charge. So we have the calcium here, a very weak bond with a partially negatively charged oxygen, and in the meantime, I have carbonate in here with a complete negative charge with a really high abundance of electron cloud around it. So what happens? This bond here will out compete the bond between the oxygen and the calcium in here, which would result in the breakage of the bond between the calcium and the oxygen and forming a salt of calcium carbonate. The same deal goes with the hydrogen and the weak bond with a nitrate. The sodium comes in now with a very strong positive charge, forms a new bond with a polyatomic ion, which would be much stronger than the weak bond between the nitrate and the hydrogen, which would form a new salt, which is NaNO3. Okay? I know we made a lot of mess in here, but we're going to look at the equation in a second. So that's basically what happens here. We're forming now a completely new salts, and that's how the displacement reaction takes place. Okay? So the new salt that we formed, which is the calcium carbonate, it is considered an insoluble compound in water, or we can also describe it as a precipitate. Okay? So the moment the calcium and the carbonate bonds together to form calcium carbonate, this becomes a solid material and essentially drops out in your solution and starts forming solid material at the bottom of your beaker or at the bottom of your flask. And it would look like this. And that's what happens after the reaction. Okay? So this is a double displacement precipitation reaction because the salt that has formed in here, it's insoluble in water, formed a precipitant solid material at the bottom of your container or of your solution. Okay? So if we look at the overall equation right here, we have the calcium nitrate reacting with a sodium carbonate. Okay? And again, this is a double displacement reaction. So if I were to mark my A, B, C, and D, so that's A, B, C, and D. So my A will be calcium, my B will be nitrate. And again, I'm taking the whole polyatomic ion. My C will be sodium. My D will be carbonate. Okay? So A with D and B with C. Okay? So calcium carbonate and sodium nitrate. This material is a solid material, so we call this one as a precipitate. And that's what we saw earlier settling at the bottom of the beaker or at the bottom of the flask. Okay? What we need to learn from doing precipitation reaction, we need to predict the solubility. So we need to determine our A, B, C, and D. So what I'm going to suggest to you that the moment that you see an equation during the exam or during the practice, please label your A, B, C, and D. There is no shame of doing this. Try not to jump ahead and try to do the double displacement, at least in the beginning of doing this. Later on, maybe you get more comfortable, you can then do it. But in the beginning, make sure to label your A, B, C, and D's. So that way it's easy. Okay? Then you will determine the A, D, and the CB formula on the product side. Okay, so at this point, these are your products. And then you remember to correctly form the ionic compounds that have no net charge. So the charge that you're forming on these ionic compounds must have no charge on top of it. So the net charge has to be zero. We'll do an example and you will see exactly what I mean by this. Then you'll have to determine the solubility of your product, which is the AD and the CMB. If both products are soluble, then you will give them the symbol AQ, which means it's an aqueous solution. Then you will describe this as no reaction. So let's say that you have ABC, AB plus C and D. And then you realize your AD, for example, is an aqueous solution, or it's soluble in water. What you need to do is you need to write no reaction and you stop right there. You don't need to worry about balancing the equation. You don't need to worry about doing the double displacement or writing down the products. You can just stop right there, and you will still get a full credit on the exam or on the homework. Okay. So the $1,000,000 question is, how would I know the solubility? How would I predict the solubility of my products? And the answer is right here. So this is the table that you will need to predict solubility. And you'll have to memorize everything on this table. No, just kidding. I'll give you this table during the exam. Okay, so you don't have to memorize all this, but we need to know how to read this and how to interpret the information and the data in this table so you're able to predict the solubility of your products. Okay? So first, we have the category, we have the ions, and then the solubility of these ions, and then you have an example. Okay? So, for example, let's look at the first one, which is a group 1 metals in the periodic table. So, when we're talking about a group 1, which was talking about the sodium, we're talking about the lithium, and all those guys below them on a group 1 in the periodic table. All the salts that has group 1 in the periodic table will form soluble salts with no exception. Okay, so anytime you see a salt that has sodium, for example, it will be soluble. Okay, so I'll give you an example. So let's say that you do your A, B, C, and D, and you're writing down your products, and you realize in your products there is a sodium salt and there is a lithium salt. That means they're both aqueous, then there is no reaction. Okay, let's go back. So group 1 in the periodic table always form soluble salts. Okay, they're they don't form precipitate. In addition to the group 1, you have the ammonium from the polyatomic ion. So you have to keep that in mind as well. When it comes to soluble anions, you have the nitrate. Okay, you have the nitrate, and also you have the acetate. The acetate and the nitrate always form soluble salts all the time. Example, you have the bismuth nitrate, for example. It always forms soluble salts without any exception. So every time you see the acetate or the nitrate in a salt, then you know it is a soluble salt. When it comes to the chlorine, bromine, iodine, and also the sulfate, usually soluble, which means that we have exceptions, okay? So for the chlorine, bromine, and iodine, they are soluble with some exceptions, including silver and lead, okay? So chlorine, bromine, and iodine, so something like NaCl will be soluble, okay? So this will be aqueous. Oops, come on, okay? Um, on the other hand, something like AgCl will be solid, okay? Because silver is the exception. Same thing with PbCl2. So this one will be solid as well. There's the examples. Sulfate, it is soluble with some exceptions, including barium and lead. So for example, for the soluble salts for the sulfate, iron sulfate will be soluble. Barium sulfate will be solid, will not be aqueous. Okay, this is insoluble. And every time we say insoluble, that means it's solid. Okay. Um, Usually soluble, you have the carbonate, the phosphate, and the hydroxide. They're usually insoluble, so every time you see them, you should almost assume that it's insoluble with some exception, except when it's bonding to group 1 in the periodic table, or the ammonium, which basically goes back to the first point that we talked about right here. Okay, so this is the chart that you will need when you are predicting solubility for precipitation reactions. This piece of information will be given to you during the exam. So that's when it comes to predicting the solubility of our product in a precipitation reaction using this table right here. Let's take a step back and see where is the solubility prediction stands in the whole process of writing a balanced chemical equation for a precipitation reaction. So first, you have to remember to determine your A, B, C, and D. So you'll look at the salts on the reactant side, and then I'll have to label our A, label our B anion, and then C and D, the cation, and then the anion as well. Okay. Once you have determined your A, B, C, and D, you'll have to do the double displacement reaction, which means switching partners. So B will break off from A, will bond with the C instead, and D will form with the A. At that point, you have your products as well as your reactants. Next thing, what you need to do is you need to predict the solubility of your AD and the C and B, the new products that you were just able to form in this precipitation reaction. How do we know the solubility of my products? This chart right here. Okay. When you predict the solubility, it really accepts two outcomes. Either one of the salts is forming a solid material or a precipitate. Then we'll talk about a step 4 and 5 and beyond that. Or both salts are actually soluble in water. Okay, so in this case, you will just write no reaction. Soluble means it's aqueous. So you follow the chart, you will look at your cation and anions forming the new salts, and then you would refer to this table right here. If you're forming a soluble salts, then there is no reaction. You stop right there. You don't have to worry about it. You don't have to worry about any further steps as far as balancing the equation or trying to write the physical state of all the products or the reactants. You just stop right there and call it no reaction. If there is a solid material forming, however, or you have a precipitate, then you'll have to follow to step 4. Okay. The next step after you predict you predict your solubility, you'll have to balance the equation. So just like how we did in previous examples, balancing the equation, so you make sure that your number of atoms of X element on the left side equal the number of atoms of that same element on the right side of the equation. So the number of atoms on the product side equal the number of atoms on the reactant side. Okay? Following the steps that we talked about earlier in balancing the equation. Once you do the final, once you balance the equation, what you need to do, you need to make sure that your reactants has been separated by a plus sign. Okay? This is kind of like one of the basics when it comes to writing a chemical equation. Um, You have to make sure that your products and reactants are separated with a single arrow pointed from left to right, from the reactants to the product. And then you'll have to make sure that the formula of the product's also separated by a plus sign. Most importantly, you'll have to add the physical state for all the compounds, for all the molecules you have in this chemical equation. Okay, so if it is something insoluble, you will add an S, which means it's a solid material, or soluble. Then you'll have to write AQ, which means aqueous. Okay, at that point you'll have to make sure the equation is balanced, and that should be the end of the story. All right, let's put everything that we just talked about into practice and try to do this example. So here we have NaCl reacting with lead nitrate. First, what I need to do is I need to write my arrow, so it's pointing from left to right. What I need to do also, as I mentioned earlier, I'll have to determine my A, B, C, and D. So my A, B, C, and D. So my A is sodium positive. My B is chloride negative. Now, how do I know what is the oxidation number, in this case for the sodium and for the chloride? So sodium is part of the group 1 in the periodic table. And if you refer back to the periodic table, in our lecture regarding the periodic table, all the elements on the first group on the periodic table, they always have a positive 1 oxidation number. The chloride, which is part of the halogens on the periodic table, which is all the way to the far right, next to the halogen, next to the noble gases, I'm sorry, all those folks, they will always have a negative 1 oxidation number. So chlorine, like the iodine, like the bromine, so on and so forth. And sodium as well. So sodium, like the lithium, they also belong to the same group in the periodic table. Sodium, lithium, potassium, so on and so forth. Okay? So, my C now, Pb. And Pb is a positive 2. You can tell this from the chart that it will be given to you in the exam right here. So this is lead right here with a positive 2 oxidation number. So that could be a way of telling the oxidation number for the lead. Or in the same time, if you look here and if you pay attention to the 2 down here for the nitrate parentheses, that means it's the swapping of the oxidation number between the Pb and the NO3. Because remember, the NO3 is a negative 1, right? So the fact it's a 2 in here, that means this 2 okay, this 2 must have come from the oxidation number for the lead. That's how we write the molecular formula for the lead nitrate. Okay? We did that when we talked about the oxidation numbers, I think a couple lectures ago. So if you're not sure about this one, you can either email me, ask a question, or you can refer back to my lecture a couple weeks ago. Okay, so that's a technique that we use to by looking at the oxidation numbers of the elements, how to predict the molecular formula. Okay, so that's my A, B, and C. Now when it comes to the nitrate is NO3 with a negative charge. How do I know what is the oxidation number for the polyatomic ion for the nitrate? That goes back to our polyatomic ion chart, which is somewhere here. Okay, right here. So here's the nitrate. That's why this table here, it is really important to memorize and be familiar with all the names and all the oxidation numbers, because you will need it in events like this. All right, let's go back to our example. So now that we have Now that we have wrote our A, B, C, and D, what we need to do now, we need to form um, the new partners, right? The new couples. So now A is going to go with D, and B is going to go with C. So my new products is going to look like this. A and D, so that's NaNO3. Now, we always have to bear in mind the oxidation number and um, the total oxidation number for the molecule. The total oxidation, the total charge over the molecule for the sodium nitrate has to be a net zero, so there is no charge for the molecule itself. So that's why when we are trying to write the molecular formula for the NaNO3, we will swap the oxidation numbers like this, and it would be NaNO3 like this. Okay? So the next one that I have, plus B and C. So lead chloride. Because a chloride is negative and lead is a positive too, we are going to swap the charges. As a result, the molecular formula for the lead chloride would have two chlorides and one lead atom. Okay? So now I have decided I was able to figure out my A, B, C, and D, so this step is over. Now I am also able to write down my AD and CB or BC. So this is step number 1. This is step number 2. Now what we need to do is now we need to predict solubility, correct? So how do we predict the solubility? We can just go by the chart that we just went over a second ago. So first, let's do the NaNO3. So Na is from group 1 in the periodic table, and based on the chart that we just looked at, all the elements, all the cations from group 1 in the periodic table, they always form soluble salts in water. If you are not sure, if for some reason that you use the chart and you're getting confused a little bit, always think of NaCl. NaCl always soluble, right? The table salt. So it's basically the same thing. So NaNO3, because sodium is from group 1 in the periodic table, this will have an AQ symbol, which means it's aqueous. It's soluble in water. Let's look at the PbCl2. The PbCl2, or the lead chloride, this guy here will be a precipitate, will be solid. But let's try to use the chart for this one. Okay. So my anionic part is the Cl, the chloride right here. So the chloride soluble with some exceptions, including the lead, including the silver and the lead, which means the lead here is going to form a solid salt, a precipitate in this specific reaction. Okay, so PbCl2, it is going to be a solid. It's going to be a precipitate. So what I need to do is I'll have to write this as an S. Okay, so this will be my step number 2. Oh, sorry. Well, this will be part of my step number 2, determining the solubility, or this probably will be step number 3. All right, let's make sure that we're following exactly the same procedure. So we predicted the solubility, and now we're right here. Now, number 4, we'll have to balance the chemical equation. So now we predicted the solubility, we wrote our A, B, C, and D, we formed our products. What we need to do is we need to balance the equation. How do we balance the equation? We'll have to first write down our elements. On the products, as well as there's Cl, there is Pb, and there is NO3. So the NO3, I'm taking this as one unit because it's a polyatomic ion. And we'll have to write our inventory of atoms. Okay, so for the reactant side, this is the reactants and this is the product. For the reactant side, for the sodium, I have one and I have one on the product side. There is one, there's one. That's easy. For the chlorine, I have one chlorine, which is right here, and I have two chlorine. So there's one and there's two. Then in order for me to balance the number of chlorine on the product side, I'll have to add a coefficient of 2 right here. So the chlorine is balanced now on both sides. So I can cross this one out and call it a 2. Now, in the same time, this 2 here, it is going to affect the count of atoms for the sodium, correct? So, because this coefficient also applies for the sodium. So, sodium is, on the reactant side, is no longer a 1, it is now a 2. On the product sodium, I have only one sodium right here. So what I can do is I can just multiply this by 2. So I'll multiply this by 2. So sodium now and chloride has been balanced up to this point. Let's look at the lead. So lead, I have one lead right here, and I have one lead on the product side. So that's another one. So lead is all balanced. I don't have to worry about it. Let's look at the nitrate as one unit. I have 2. I know my writing is masking the parentheses here. So I have 2 of the nitrate, and I have 2 of the nitrate down here. So the nitrate is also balanced. So my final balanced equation would look like this. Let's clear this off. Okay, so this one, let's make it nice and clean. 2NaNO3, and that's aqueous. We have 2,1-ACl. All right, let's clean this. This one here will be PbCl2. This one will be solid. So when it comes to the net ionic equation, we only write the net ionic equation for a reaction that forms a solid material or forms a precipitate. Now, obviously, if all salts are being in the aqueous or all being soluble in water, then we would call this as no reaction, and we wouldn't even be getting to the stage of balancing the equation. So, when you're writing precipitation reactions, the net ionic equation is always required, specifically when you're forming a precipitate at the end. So let's try to write the net ionic equation for this equation. When we say aqueous, that means the salt for the NaCl is basically existing in a form of cations. And okay, let's make this smaller a little bit. In a form of cations and anions. That's when we talked about NaCl. The NaCl dissociate the bond between the Na and the Cl. It dissociates, and now it exists in a form of cations and anions because of being an aqueous, soluble material in water. Okay, a soluble compound. Because I have a coefficient of 2, I have to remember to keep this in mind. Okay, now the next one I have is the lead nitrate, and because it's aqueous as well, that means it will exist in the form of cations plus anions. So I'm keeping my polyatomic ion together, and this will be a negative. That's what we know where the negative charge is coming from the polyatomic charge. And the 2 here, that means the lead has a positive 2 charge. Oops. Okay. Let's go to our products now. For our products, I have NaNO3, and this one is also aqueous, so this will exist in a form of cations of sodium plus anions of nitrate. But because I have 2 in here, I'll have to factor that in my cations and anions count. All right, I'm crossing it down here because I'm running out of space. Let's look at the lead chloride. This one is a solid Because it's a solid, the cations and anions will not dissociate from each other. However, it will remain intact as PbCl2. That's why it's a precipitate. It's not going anywhere. It's not dissolving. So the cations and anions remain closely attached to each other, unlike the aqueous or in the compounds that it's soluble in water. So what we can do here, we can now cancel the cations and the anions on the product side and the reactant side as long as they exist on both sides. Okay, for example, if you look here at the sodium, I have a sodium here and I have a sodium here, and I have two of each. So what I can do is I can cancel the sodium out. If I look at the chloride at the same time, I have two chloride, but I don't have any chloride in the product side, so I can't really cancel the chloride. So the chloride will have to stay. Lead is the same issue here, which is right here. So I don't have any lead on the products as part of my product. So the lead will have to remain in my reactants. It cannot be canceled out. The nitrate, however, yes, I can cancel this one because I have, oops, I forgot my 2 in here. So there should be a 2 in here. And that's from this 2. Okay? So 2 of the nitrate is going to cancel out with a 2 of the nitrate as well. And there should be a negative charge here as well. Okay? So my net ionic equation would at the end be as such: 2 chloride, because the chloride here did not cancel, plus Pb, that's the other ion that I did not cancel. So that's P, oops, let's clear this one off. I don't like my P. That P was not as elegant. Okay, come on, red. So that's P, B, and that's 2 positive. Never forget your oxidation numbers. Do I have any other ions on my reactant side? No, everything has been canceled. Okay, sodium has been canceled. The nitrate has been canceled. Only the PbCl2. So PbCl2. Don't forget your S. So this is the net ionic equation. The ions that we just canceled, the sodium and the nitrate, and the sodium and the nitrate on this side, we call these as spectator ions because these ions are not really getting involved in the formation of the solid material and the formation of the precipitate. Those guys are basically just sitting there and watching the whole process take place between the chlorine and the lead to form the precipitate of the lead chloride. Okay? So we call these spectator ions, and keep that in mind as well. Let's try another example. So now we have ammonium chloride. Here's my arrow. All right, green. Let it be green. Here's my ammonium chloride and calcium sulfate. Both are aqueous, but first thing first, what I need to do is I need to label my A, B, C, and D. So that's my number 1. What is my A? It's the ammonium. So that's NH4 positive. This is also part of the polyatomic ions. So if you're not sure about the charge of this one, you can always refer to the polyatomic ion table. For the chloride, that's going to be my B. Moving on to the next molecule, calcium, and that's 2 positive because calcium is on a group 2 in the periodic table. That's why you'll have to know how to use the periodic table. The periodic table offers all the information you need when it comes to the oxidation number, especially for group 1 and group 2. And we go to the nonmetals as well. If you look at the nitrogen and the oxygen, so on and so forth, everything is right there in the periodic table. So please, you have to be familiar with how to use the periodic table. Otherwise, this will be a whole different game here. All your oxidations number will be incorrect. The molecular formulas will be incorrect. And unfortunately, you're not going to be able to answer this. Okay, so please be familiar on how to use the periodic table. Getting the oxidation numbers at least. Okay, so that's for the calcium. For the sulfate, so that's SO4 2 negative. And that's again from the polyatomic ions and the periodic from the polyatomic ions table. So number 2, what I need to do is I'll have to form my AD in B and C. So first product that I will have, I'll have ammonium sulfate. But this is incomplete because if you know NH4 plus SO4 2 negative, what I need to do is I'll have to do the swapping, right, in order to write the correct chemical formula. So will be NH4 parentheses 2 SO4. This is the correct molecular formula for the ammonium sulfate. Okay? Plus, if you go to the next one, which is B and C, this will be calcium chloride, but this one will be A2. How do we figure out the molecular formula for the calcium chloride? So this will be calcium 2 chloride 2 negative. Oh, I'm sorry. Oops. Negative 2 positive. You'll do the swapping. So I'll have calcium chloride as such right here. So the next thing, what I need to do now, I have wrote down my A, B, C, and D. Now I have also predicted my products here. So now I have my AD plus B and C. So step 2 is completed. I think everyone should be really getting to this stage of the game. I think this is really easy one. You just have to be really careful, especially when writing the chemical formula and getting your oxidation numbers correct. And it's I don't think really it's that complicated. Next, once you figure out your products, now we'll have to determine our solubility. So we know if we have a complete, if we so we know if we have a precipitate or we don't or we have no reaction if everything is soluble. So let's go back to our solubility chart and now determine if the ammonium sulfate is actually soluble or not. All right, let's go back to our table. So looking at this table here, we can tell that ammonium is actually part of the group 1 metals that always form soluble cations, and it has no exceptions. When I say it has no exceptions, that means the ammonium sulfate is actually going to be soluble. So when we say soluble, all right, let me start this again. NH4 2 SO4. That means we will write aqueous for this one. It is soluble because the ammonium is part of the group 1. Well, it's not part of the group 1, but it belongs to on that chart, it belongs with the group 1 cations that they always form soluble salts regardless of what they are associating with. Okay, so it doesn't matter if it is a sulfate, it doesn't matter if it's a chloride, doesn't matter if it is a nitrate, the ammonium always form soluble salts in water. So that means we call it aqueous. Let's go to the calcium chloride. So and try to figure out from the table if the calcium chloride is going to be soluble or not soluble in water. So chloride right here. This is what we're targeting. So chloride, soluble with some exceptions, including silver and lead. And calcium is neither silver nor lead, which means calcium chloride is going to be soluble in water as well. So this one is going to be aqueous. So both the calcium sulfate and the ammonium chloride form two salts that are soluble in water and are forming no precipitate. There's no precipitation reaction happening in this case because there is no precipitate has formed. So what we do in this case, we just write no reaction or no reaction, and you don't have to proceed any further. You stop right here. Okay? So best case scenario that I'll give you all no reactions in the exam or in the final exam. Now, of course, that's not going to be the case. So if you see, I'm telling you right now that if you see in the exam two equations or three equations and you're getting no reactions for all of them, I'm not going to be doing this because I'm going to have to, and I would like to examine your skills when it comes to balancing the equation, predicting the solubility, predicting the oxidation number, or writing the molecular formula. So that's for sure. I'm not going to give you all three questions as no reaction. At least one or two of them will have a precipitation reaction that actually taking place. So I can see how you can handle the problem from beginning to end, all the way to the net ionic equation. Okay. So this essentially takes care of everything in this unit. Concepts that we covered, we talked about balancing the chemical equation, how to write our inventory for the reactants and for the product, how to add a coefficient. We also got introduced to different techniques of balancing the equation using fractions and using the subscript as a way to determine your coefficient, so on and so forth. We also learned about predicting the products of double displacement reaction, okay, determining your A, B, C, and D, and when you do the double displacement. And we also predicted the ionic solubility for the salts that are formed from a double displacement reaction. We just did a couple examples. And then at the end, we wrote down the net ionic equation and how we cancel the spectator ions on the reactant side, and on the product side, those are the ions that aren't really involved in the precipitation reaction or in the form of the precipitate. That's why we call them spectator ions. They're just sitting around and watching the whole process unfold. Okay, so this covers everything in Unit 5. Obviously, there will be a homework. Please try to do as many um, um, practice problem as possible, even from the book. If you guys want to try some, or if you want to send it over to me, if you are having a hard time, I can always help you out. The more practice problems you can do with these, the more familiar you become. Hopefully you don't make any mistakes. Okay.